Okay, this is Physics Chapter 14, Lecture 3. In the book, we're starting on page 473, 472, 473. And in your notes, we're in the middle of page 4. Okay, so this lecture is about a capacitor. So a capacitor is a device that stores charge until it's needed. So just a basic capacitor diagram. Let's say we have a wire that goes to a metal plate. All right, so this is a wire. Okay, those are metal plates. And let's say the charge coming in is a negative charge. So on the other plate, a positive charge will develop because positive is attracted to negative. Now, those charges can't flow to each other because those plates are separated. Okay, so they're separated by some sort of insulator. Now that insulator has a name. It's called a dielectric. And it can be air. It can be glass. It can be plastic. It just depends, okay? But the charge can't flow, but there's a lot of surface area for the charge to reside while it's waiting to flow. So capacitors in smaller devices can also be made like a spiral. All right, so that piece of metal might be bent like that, and that'll save a lot of space. You'd have the negative charges on one side and the positive charges on the other side of the piece of metal. All right, so in the description of this video, I will have a link to a capacitor animation that shows you how a capacitor charges and discharges. So make sure that you watch that video. It'll make a whole lot of sense for you, what the purpose of a capacitor is. But one note to make at the bottom of page 4 is if the charge on the positive plate is, let's say, 10 coulombs, which is an awful lot. It doesn't matter. Okay, the charge on the negative plate is minus 10 coulombs. So it's the negative of, you're going to have the same magnitude of charge, just different signs, depending on which plate that charge resides. Okay, if you'll look at the top of page 5, we will get into the math of capacitance. So we have an equation, and that is voltage is equal to charge over capacitance. All right, and the unit for capacitance is farads, after Michael Faraday. So we just use an F. And you can also have the change in voltage is equal to Q over C sub Q. That's the one we'll use most. Okay, so we've got a bullet list up at the top of your notes that tells you what each of those means, and you already know, honestly, what they all mean. So let's look at 14.8 on the bottom of page 473. So if you'll read along, it says, if a 4.6 times 10 to the minus 6 farad capacitor must be used to generate 125 volt electric potential, how much charge must it store? Okay, so we'll start with this equation. Voltage is equal to charge over capacitance. We're solving for charge for Q. So Q is equal to voltage times capacitance. So that's 125 volts times 4.6 times 10 to the minus 6 farads. And that is 5.75 times 10 to the minus 4 coulombs. All right, so just a basic problem to try to get you to memorize the capacitance equation. So let's look at 14.9. All right, so this is on page 475. So reading along with that, it says a proton, and it gives the mass of the proton and the charge, is placed at the edge of the positive plate of a 3.4 times 10 to the minus 6 farad capacitor. If the capacitor holds 12 millicoulombs of charge on its positive plate, how fast will the proton be moving when it reaches the negative plate of the capacitor? If you want to know how fast, you're going to have to get the change in the kinetic energy, because that's 1/2 mv squared. That's our formula that has velocity in it. In order to get the change in kinetic energy, you need to get the change in potential energy first. So remember that change in potential energy is equal to the moving charge Q times delta V. All right, now we can get delta V. It's big Q over the capacitance. And in this problem, the big Q, which is the charge on the capacitor, is 12 times 10 to the minus 3 coulombs. And the capacitance is 3.4 times 10 to the minus 6 farads. All right, now you know that it moves to the negative plate of the capacitor. So it's moving from the positive to the negative plate. So this is a really important concept to realize. So that's 3,529 volts, but we have to make that negative. So make a note here. Moves to negative plate. So that change in voltage is negative. Now that we have the change in voltage, we can get the change in potential energy, because the change in potential energy is equal to the little q, that's the moving charge, or the charge of the proton, 1.6 times 10 to the minus 19 coulombs, times this negative 3,529 volts that we just calculated. So that's negative 5.65 times 10 to the minus 16, and the unit for energy is joules. Well, if the change in potential energy is negative 5.65, the change in kinetic energy has to be positive. We lost potential energy, but we gained kinetic energy, 5.65, assuming no losses, times 10 to the minus 16 joules. And that is equal to 1/2 mass times velocity squared. And the mass of a proton, of course, is tiny, but we'll put it in, 1.67 times 10 to the minus 27 kilograms times velocity squared. So velocity, finishing this up, is going to be the square root of 5.65 times 10 to the minus 16 joules divided by 1/2 times 1.67 times 10 to the minus 27 kilograms. Easy to make a mistake in your calculator there, but if you don't make that mistake, you'll get 8.22 times 10 to the 5th meters per second. So try that in your calculator. Less than the speed of light, so it is plausible. Okay, so we used up that whole board. So pause it if you need to continue to copy things down, and I will finish out this chapter with the next on your own. All right, if you'll turn your page to 476, we'll finish up with on your own 14.10. And if you'll read along with me, capacitors are used by physicists to accelerate ions so that their behavior can be studied when they collide with other ions, such as the Large Hadron Collider or the collider at CERN. You can look those up if you're interested. A physicist wants to get an ammonium ion traveling with the speed of 1.2 times 10 to the 6 meters per second in order to collide it with another ion. If the physicist has a 2.3 times 10 to the minus 6 farad capacitor, what charge must it hold for the experiment to work? Okay, this time, one clue to how to solve this problem is that you've been given a velocity. And in this chapter, the only thing that we need velocity for is to calculate kinetic energy. So kinetic energy is 1/2 times the mass, which the mass of this ammonium ion is 2.8 times 10 to the minus 26 kilograms, times the velocity squared, and the velocity is 1.2 times 10 to the 6th meters per second. Don't forget to square that value. And you'll get 2.02 times 10 to the minus 14 joules. So this ion is speeding up, so that's a gain in kinetic energy. So the change in potential energy is going to be the negative of that. We lost potential energy, negative 2.02 times 10 to the minus 14 joules. And we're going to set that equal to Q delta V. All right. So we can solve, we're going to need to get delta V. We can solve for delta V by dividing that energy by the charge on the ammonium ion. Okay, so change in voltage is minus 2.02 times 10 to the minus 14 joules divided by Q. If you'll look in the text of the problem, that's 1.6 times 10 to the minus 19 joules. So you get a change in voltage of negative 1.26 times 10 to the 5th volts. Now we know that the change in voltage is equal to Q over the capacitance. And it asks us for Q. So Q is going to be equal to the change in voltage times the capacitance. Right? The change in voltage, negative 1.26 times 10 to the 5th volts. The capacitance in this problem is 2.3 times 10 to the minus 6 farads. All right, so that will give us negative 0.29 coulombs, and that's on the negative plate. And so on the positive plate, we'd have plus 0.29 coulombs. All right, and that finishes out the math for chapter 14. You can finish your reading out, and you should be able to finish up the review questions and the practice problems based on this lecture. Okay, so you should be able to do review questions 8 through 10 and practice problems also 8 through 10. And then, of course, all the extra practice problems when you complete that. So this starts on page 485. All right, so there's another chapter in the books, and I'll talk to you next video.